Let's look at another example of a two-sample t-test, and then also kind of elaborate and see how would we adjust this to do a two-sample confidence interval. So example 2 from the packet says, let's say 50 men and 50 women were selected at random and data on their average study time was collected. So similar to example 1, let's say we increase the sample size and we do the same sort of test, and we have a good SRS of data. It says for each set, the mean and standard deviation was obtained and calculated and is given as following. So it says start by calculating the standard error and the two-sample T-statistic. And we could do this all in one step just by using our formula. T is equal to x1 bar minus x2 bar, divided by the standard error, which remember is s1 squared over n1 plus s2 squared over n2, and the square root of all of that. And it would be faster just to calculate this with a calculator. So let's just go ahead and take a quick shortcut. So again, we need to go stat test two-sample t-test. If we were to plug all these things in, we'd have 118 minus 155 divided by the square root of 72.8 squared over 50 plus 50.8 squared over 50. And doing all that is fine and all, but we'll just use our calculator's feature. Get that all in there. And we'll operate under the same assumption that we just want to see if their study time is different, aka a two-side test. Calculating all of that, we come up with a test statistic of approximately negative 2.95. And with a calculator, it says our p-value is equal to approximately 0.004. And if we were to look it up in table C, we don't need you, then we are looking for 2.95. And remember, degree of freedom is 1 less than the minimum. Since they're both 50, the degree of freedom would just be 49. So we'd go to row 49, which there is no such row. So we go to the closest row, which is 50, and we'd be looking for 2.94. 2.94 would be very close to here, slightly larger. So it's going to be somewhere between these two elements on the two-sided p. So if we go down to the very bottom right here, it's going to be very close to 0.005, somewhere between 0.005 and 0.002. Oops. If you're wondering on an exam, how should you answer it, you can do it either way. I'm not forcing you guys to get a calculator and learn how to do it with this calculator, but it's as I've been saying all semester, it's suggested, but it's fine if you don't, because you can always use the table. The table, in my opinion, is a little bit more frustrating to use, but we would get a p-value is between, this would be the other sort of answer we get, 0.002 and 0.005, which is less accurate than calculating a more specific answer with the two-sample feature. Anyways, and then finally, we could answer the question either. And also remember, it doesn't really matter specifically what our answer is, because it's all about what is our alpha level, what's our significance level. And if we're asked to see how strong is the evidence, is it significant at an alpha level of 0.01? Well, both of these numbers are below 0.01, so it's somewhere in there. So we know that our true p-value is less than alpha, even without looking at it in a calculator. So basically our p-value is less than alpha, which means that it is statistically significant. So yes, this is significant evidence. And again, what's our conclusion? Now, the conclusions are very slightly different for two sample means. And remember, it's always a check of whether they are different or not. So this particular data set provides us with significant evidence to say that the mu1, again, kind of recalling h sub 0 is that mu1 is equal to mu2, and h sub a was that mu1 is not equal to mu2. And basically, when we have significant evidence, we reject the null hypothesis. And all that means is basically our conclusion is that the means are not the same, and we rule in favor of the alternative hypothesis because there's less than a 1% chance that we will be wrong. So we're basically we're very certain of this. And again, this is kind of our conclusion that their means are different. So kind of answering the question, yes, we are in favor of H sub A in this particular case. Now, when you do get significant results, we could actually measure. One of the things about this is the only conclusion we have is that they have different study times. But what if we actually wanted to formulate like a confidence interval or a set of numbers for them? Obviously, we could use our obtained sample means and say, okay, men study on average of 118 minutes, while women study on average of 155 minutes. But we could kind of develop a confidence interval for how much more or how much less do men and women study from each other. And we could do that by using a confidence interval formula. And noticing the difference between these, like if we look at the confidence interval from chapter 10 for a T confidence interval, it was just we took the sample mean and then added our critical value times the standard error. And notice it's exactly the same for two means. What we do is we replace, instead of measuring using the sample mean as our unbiased estimator, we use the difference in our sample means as the starting value for our interval. So that's one notable difference. And then we add or subtract the critical value multiplied by the standard error. And notice we've just replaced the standard error for a single sample with that of a two sample. Again, it's exactly the same structure. It looks quite a bit more complicated, but at the end of the day, it's pretty much the same deal. And again, we could calculate this by doing the math. So we have 118 minus 155. Notice what this will do is this, since men are listed first in this study, what we're going to get is an answer that shows us how much less men study than women, because the average, the difference between the means is going to be a negative number. So you can get negative confidence intervals. That's nothing to worry about in this case. And we want to do a 90% confidence interval, so we would need to figure out T star for this. And again, we can do that with table C because we're using T distributions. The thing to remember is we're a DF of 49. And so when we're going to our table, we want to make sure to use the best row we have, which is 50. And we just want to go to a 90% confidence level. So that's going to be our fifth column. So 1, 2, 3, 4, 5. We should use a T star of 1.676 for our critical value here. Okay, so this would be 1.676, and this will be all multiplied by the standard error, which I asked us to calculate this above, and I didn't because I was being a little bit lazy, and now I wish I would have. But we'll go ahead and type that all in. It's just going to be the same thing we have from right there. So let's go ahead and find the upper end of our confidence level. So we have 118 minus 155 plus 1.676 multiplied by the square root of all that stuff. And that would be 72.8 squared divided by 50 plus 50.8 squared divided by 50. All of that looks to be in the square root, so we're good to go. And if your calculator has trouble with this sort of thing, or it's not, I'd suggest just getting a better calculator. But anyways, we did all the math, and so the upper end of our confidence interval will be negative 15.96. And to do the lower end, I just need to change that plus to a minus. And this would give us negative 58.04. And again, negative numbers should make sense because men studied less than women and men came first. So again, this is a measure of how much less men study than women, and we have a 90% confidence interval. And also, if the question of mu1 minus mu2 is kind of throwing you off, all this is saying is that we don't know what the true difference. Remember, mu is the true mean of those two populations. We don't know the actual averages of study times for all men and women. But we're using our data x1 and x2 bar as a reference for this, as a inference about the actual data. So again, it's like sample is an inference about the actual, and that's always what confidence intervals do. So again, what we conclude here, again, sort of using the sort of cookie cutter statement for our conclusion, is that we're 90% confidence. Notice this says that women spend between blank more minutes than men, but since this was less, basically this means men study 58 minutes or 16 minutes ish less than women. But we could rephrase this, as well, women study more than men because men study less than women. Also, just to mention, this data is purely fictitious and it's all made up just to illustrate a point. So I don't know if men study more or less than women in actuality, but this data, which I made up, seems to indicate one direction or the other. And, we could say that there is a difference, statistically significant data to indicate this, but it's not real data. So a lot of times in stats, I make up data to try to just help you see how the math works. But obviously you could then use this to formulate your own statistical experiments or studies. But anyways, let's just round this to the nearest minute because it's pretty darn close. But basically women spend somewhere between 16 to 58 more minutes than men. We don't really know exactly, but that's always what a confidence interval tells us. The last thing I wanted to mention is when should I use a two-sample T-statistic, kind of like what I mentioned at the end of chapter 20, where if the data set's too small, you want to be very careful to make sure the original data is normal. But if the sample size is large enough, it doesn't even matter if the sample's normal or if there's outliers or whatever, it's good to go. And basically you can take a lot of the same rule of thumbs and apply them to two-sample tests as well. But basically, to sort of summarize all of this, two-sample tests are even better than one-sample methods, just in generally speaking, and more accurate as well. And we can use these procedures for non-symmetric data in similar rules. Like if you go ahead and look at the rules, this is exactly the same thing as from the last thing. But one of the issues is that we're dealing with two different sample sizes. But basically, you can use the same guidelines by using the pooled data, but basically by adding up the sample sizes. So like in the first example we did in this chapter 21, we had 10 men and 10 women. So our total sample size would be 20. So basically, that would be good to go in the bracket of, well, we can use T procedures except when there were outliers and skewness. So maybe we should not have done a T test from example number 1 of chapter 21, because there were outliers. It wasn't perfectly symmetric, but it was sort of symmetric. I don't know. Basically it's not as strong. I'd be more leery of the results. However, in our second, more recent example 2, our pooled sample size was 100, more than enough to use. So that data is for sure good to go. And lastly, I mentioned that the sample size does not have to be the same between your two individual pools. But it's stronger when they are equal. It will be the best, and if the data is similarly shaped between the two groups. If the data is very different and they're different sizes, it will be less accurate.